So today we're going to be graphing piecewise graphs, and we're going to be graphing true piecewise graphs in true piecewise notation. The only other way that you may see this notation is in interval notation, which is not going to be what we see today, but we will cover interval notation in a later video. So a piecewise graph, it changes between one spot and the next. The boundary is only included in one graph. This is shown through the inequality. Now, what that means is the fact that, again, I'm going to have this graph and it's going to have two different pieces. Today, I'm going to be graphing in pencil because we're going to need to be able to erase some of this. Now, that's strictly because of the method that I show. What I show is that I'm going to look at each one of these and I'm going to graph both these graphs in their fullness, and then I'm going to apply the boundary restrictions. So let's go ahead and let's review a few quick rules on how things work. If I have a y equals mx plus b, that's going to be a line. I know that that's going to be my y-intercept. I know that my m is going to be my slope, which is also my rise over my run. So I'm going to be graphing according to that rule. If I have something that's like y equals the absolute value of x, I know that if I add anything inside the parentheses or inside the brackets, that's going to be moving to the left. If I subtract anything inside, that's going to be to the right. I know if I add anything outside, that's going to be up. If I subtract anything outside, that's going to be down. So I'm going to follow these sets of rules when we're going through this today. So let's take a look. So again, I'm going to be graphing these in pencil. I know that this top one is going to be y equals 1/2 x. That's going to be a line according to my rules. There's no y-intercept, so I have an intercept at 0, 0, and my slope is going to be up 1 and over 2. So if I go up 1 and over 2, I'm going to create a line just like that. I'm going to go down 1 and back 2 as well. Cool. So I have a line just like that. There's my y equals 1/2 x. For my other graph, y equals -x, well, that is also a line. There's no y-intercept, so it also goes to that point, but it goes down 1 over 1. So it is what we call a perfect diagonal going down. Cool. Y equals -x. Awesome. So I have these two graphs, and what I need to do is now I need to plug in these boundary restrictions. So what I'm going to do is I'm going to quickly highlight, I have a boundary right at -2. So I'm going to draw a quick dotted line, which is not technically part of the graph, but it shows me, okay, that separates my graph into a right side of -2 and a left side of -2. So we're going to see, okay, which one's on the left and which one's on the right? Well, let's go ahead and let's make this one in red. My 1/2 x, which is the one that's sloping up, is only for x values less than -2. So it's only going to be for values less than -2, which means it's to the left of my boundary point. It's only the values over here. I don't actually look at anything on the right-hand side. So if I have that 1/2 x, I'm only seeing this little piece. So I'm going to highlight this little piece in red because that's the only part I truly graph of my graph. I don't actually include the boundary point, so what I do is I'm going to draw an open circle on that boundary point. For my other graph, I'm looking at values greater than or equal to -2. So I'm going to find my boundary point and say, hey, of this whole graph, I'm only graphing this part. I'm not graphing the portion of the graph that's less than -2, only the part that's greater than -2. So what I'm going to do is I'm going to highlight this in blue. And this actually includes the boundary point. So I'm going to fill in a circle. So that is actually my graph. And the reason why I do it in pencil is the fact that I tend to like to go over and kind of erase the part that's not included. Now I'm going to leave a little bit of a shadow just so you can see that the graph actually would go there if it weren't for these domain restrictions. But we know that the only part of the graph that we truly use is this part of the red graph and that part of the blue graph. Nothing else exists. Go ahead and list that in blue. Perfect. Kind of get the idea? Let's try a different one. So on this, I have y equals 7. Now that's going to be in my y equals mx plus b format that we have way up here. The only problem is we're missing the mx, which means that must be a slope of 0 because it disappeared. And if I have a slope of 0, that's going to be a flat line. It's going to be a horizontal line. So because I don't have 7 on my graph, I'm going to make my graph by 2's. So 2, 4, 6, 7. And my graph is going to be a horizontal line, just like that. This is my 7. My absolute value equation, we remember that that gives the shape of a V with a vertex right at the origin. And both the legs of the V are going to be perfect diagonals going to the right and going to the left. And so here I see that I have one that's less than 2 and one that's greater than or equal to 2. So I know right here there's something going on. So I'm just going to make my boundary a little thicker so we can see it. So one of these is going to be on the right-hand side and one of them is going to be on the left. So what I'm going to do is I'm going to graph my 7 in red. Well, that's going to be less than 2. So I'm going to find my graph and say, okay, less than 2. Well, less than 2 is on the left, which means that I don't deal with the right. Less than 2 is over here, which means I only have that portion of my graph. So I'm going to highlight it in red. Cool. And I don't include my point. It's an open circle, just like that. My absolute value equation is greater than or equal to 2, so I know I'm using that part of the graph, which only exists right here. And now you kind of see the reason why I graph the whole graph and then go back and erase the portion of my straight line that I don't use, and I erase the portion of my absolute value that I don't use. Now, you might ask, why do I do this? Well, if I graphed this, does this straight line look like an absolute value? Oftentimes, no. A lot of students expect to find the bend. And so what I do is I graph the full thing so I know exactly where that vertex is. And I'm like, oh no, that's an absolute value equation. We just don't see where the vertex was. Sometimes students will want to put a vertex in there and just randomly put a bend. That doesn't work, so that's why I always graph the full thing and then go back and erase it. So I have a 7, and absolute value of x. Cool. So let's do a few more. So here it looks like I have a barrier at -1. So I'm going to go ahead and I'm going to slide a value at -1. Ooh, and just realizing I actually drew my barrier a little bit too far to the right because I counted these by 2's. That barrier should actually be at the 1 tick mark because remember the barrier was at 2. So I should scoot that over. Unfortunately, I didn't in pen. So what we'll do is we'll just scooch the whole thing over. Cool. Let's take a look at this one. So if I have my barrier at -1, what I'm going to do is I have what looks like an upward line with a positive slope of 2x. It has a 0 y-intercept. So I'm going to draw a line that goes up like this, down 2/1, down 2/1, boom. So it does something like that. That's my 2x. My -3x goes 1, 2, 3/1. So it goes down like that, up 3, back 1, up 3, back 1. That's my -3x. And so I see that the lines are each split on the left and on the right. And so what I'm going to do is I'm going to say, hey, I'm going to graph my 2x, which is less than or equal to -1. So I'm going to find my barrier, find my 2x line, and say, okay, if it's less than, that's to the left. So I'm only going to graph that little piece down there. And I'm going to fill in my circle because that boundary point is included on that one. And my 3x, well, if that was less than, my 3x is greater than, which means it's the other side. Or my -3x, I should say. So I'm going to graph the right-hand side of my -3x. And I'm going to draw an open circle on the barrier because that is not actually included. Boom. And there we go. I go back and I erase the portion of the graph that isn't actually included, but I just left it in there so that I could tell that I graphed the thing correctly. There we go. We have a piecewise function of y equals 2x on one side and -3x on the other side. One or two more. What happens if I have 3 values? Well, that just means that I have 2 barriers. I have a barrier at -3, which I notice that juts up against -3, and so does the next one. So -1, 2, 3. So I'm going to have a barrier right here. I also have another barrier at 4. This one juts up against 4, and as does that one. So it's going to be right there. Cool. So I'm going to do my first one, 4, which is going to be a line right up here at the top. There's my 4. My 0 is right here in the middle. And my -1 is down there at the bottom. Now my 4, I'm only concerned with x is less than -3, which means if I go find my -3, I say, okay, am I looking at greater than or less than? I'm dealing with x is less than. So I'm looking at the less than portion of my graph, so only that little piece up there at the top. So I'm going to draw a nice thick blue line just to make sure that we get it. I'm going to draw an open circle because my point itself is not included. It's actually included in this one. My -3 is included on my 0 line. And I go from -3 all the way until 4. So I actually shade all of this in. Cool. So my 0 line, I included the 4 on the left, my 0 in the middle, which means I bet you that 1 is going to be on the right. And sure enough, yes, x is greater than or equal to 4. So I'm going to go find it, I'm going to fill it in, and shade it in to the right. Oh, and there we go. So it's not too bad. We're just going to make sure that we go back and we get rid of the pieces that we don't actually need. Cool. And there we go. I have left piece 1, I have middle piece 2, and I have right piece 3, because it says less, between, and greater. Awesome. Let's do a few more. If I have y is equal to x, I know that that's going to be a perfect diagonal right through there. Y equals 2. Well, you know what? What I see is that my barrier is at 5, so I'm going to go ahead and make these by 2s. Which means that my 2 is going to be 1, 2, 1 block up. So there's my 2. And then my 2x, that's going to be up 2 over 1, up 2 over 1, down 2, back 1, down 2, back 1. I have that. So I have my 2x, my x, and my 2. Perfect. So now I'm going to go ahead and draw my boundaries. I have 1 at -5. So remember, we're doing these by 2s. So 2, 4, and 5. So I have a barrier right there. Also, I have another barrier at 0. So I'm going to go ahead and I'm going to draw my barrier right down the middle. All I'm going to do is I'm going to say, hey, my x, I'm only dealing with values less than -5, so I'm going to find my x, find the -5, and say, hey, less than is over here, which means I'm going to cover up the stuff on the right. So I'm only doing this. And I'm including that point on the barrier. The next thing, my 2 is in between -5 and 0. So I'm going to find my two boundaries and say, hey, I'm only dealing with this little piece in between these boundaries. So I'm going to draw a nice thick line. I'm going to include neither end. Boom. I got that. My 2x, what I'm going to do is I'm going to include that to the right of 0. Anything that's greater than or equal to 0. So I find my 2x. I find my 0 point, which is going to be right here. I go ahead and I shade it. I'm going to fill it in because that is actually an included point. So I have that, and I go back and I erase the unused portions of my graph. Get rid of that part of my x, get rid of that part of my 2x, and these parts of my 2. Boom. And there we go. I have a piecewise function of y equals x, comma 2, comma 2x, given these domain restrictions. Last one. Y equals 4 is going to be a horizontal line. X plus 1, that's going to be a v that has shifted up by 1. Boom. Got that. And then -1, that's another horizontal line. Awesome. So I'm going to find my boundaries at -3. So 1, 2, 3. I have a boundary right here. And then again at 1, I have a boundary right here. What I'm going to do is I'm going to go through and I'm going to graph them one by one. My 4 is where my x is less than -3. So I find my -3 and say, hey, the less than piece is the one piece way up here. It's not included. So it has an open circle. My V shape is going to be between -3 and 1. So I actually get this whole portion of the V. And what we notice is the fact that even though that point wasn't included in my top graph, it is actually included in my second graph. And we'll talk about what that means in just a moment. My -1 is going to be down here. Boom. And there we go. We go back and we erase the portion of the graph that we didn't use. So I get rid of the right, I get rid of the right, get rid of the left over here, get rid of the left over here. Boom. And that's it. So the only thing that we have left that we're not really covering today, but it's a good point to notice, is this makes the graph continuous. We notice that even though it was not included with one of the graphs, the next graph actually did include that point. So if you were to try and trace the graph with your finger and say, this works, this works, this works, this works, this works, this works, you would never need to pick up your pen or pencil with tracing positive points. Now all of a sudden you would change direction, but what would happen is this allows the graph to stay continuous. Unlike right here, where the graph jumps from one to the next. That is not continuous, that is a break in the graph. There we go, that's all for today. So today we're going to be evaluating a function. Now, we all know how to do the math in what we're doing today. The actual algebra isn't too difficult. It's mostly just arithmetic, but what we're doing is we're figuring out how to read a function. Now, the way a function is written is what we say, f of an input equals the output. Now, the f is the name of the function, so this is the function name. The input generally is a variable that we show some sort of number, and it says, hey, I'm going to place this number as the variable. Then this is the operation. This is the thing that we do to get the output. Cool. So let's take a look at what that actually means in practice. So if I have f of 2 equals x cubed, what that means is that I'm going to take this function called f, and first off, I don't touch the left-hand side. With functions, this is not f times 2. This is saying my function, I'm going to go plug in a 2. So what I do is I go to the right-hand side and I say, hey, wherever I see a variable, plug that in. Well, I see a variable right there. So what I'm going to do is I'm going to say, hey, plug in a 2. And now what I tend to do is I like to put parentheses around it because it's going to stop us from making some very simple mistakes. So I have f of 2 equals 2 cubed. If we remember that 2 cubed is actually equal to 2 times 2 times 2, 1, 2, 3 times. If we had something like 2 to the 5th, that would be 1, 2, 3, 4, 5. We're multiplying it times itself that many times. So 2 cubed is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. So my f of 2 is equal to 8. Boom. And that's it. Apologize for the noise. They're mowing the lawn outside. And just like that, it might get a little loud from time to time. But we're going to push forward. So one of the reasons why I put parentheses around my input, or the parentheses around my variable input, is because of times like this. If I notice that I have my f of negative 4, and I'm plugging that negative 4 into everywhere where I see a y, well, I would put 4, and I would put parenthesis negative 4 minus 21. And I'd automatically know that, okay, with parentheses, I'm distributing that 4 inside. 4 times negative 4 is going to give me a negative 16 minus 21, which is going to give me a negative 37. Now, that seems pretty straightforward, but let's see what would happen if I didn't actually put parentheses. What might you be tempted to do? Well, what a lot of students will do is they'll say, okay, f of negative 4 is equal to 4 negative 4 minus 21. And they plugged in the negative 4 just like that. What you might read that, did they plug it in correctly? Kind of, sort of. But because they didn't put parentheses around their 4, it looks like I'm taking 4 minus 4. I'm no longer multiplying, all of a sudden I'm subtracting. And we can't change operations like that willy-nilly. So I put parentheses around it to stop us from making mistakes like this. Let's go ahead and let's not do it that way. And another one of the things that we have is that with a function, it doesn't matter how many times I see the variable. If we notice here, I have a variable twice. I'm going to plug negative 10 into each one of those. So what I'm going to do is I'm going to take a negative 10 and I'm going to square it plus 9 times negative 10. So my f of negative 10 is equivalent to this. Now another rule, if I take this and I say, okay, I'm squaring this, we remember that that's negative 10 times negative 10, which is going to net us a positive 100 minus 90. Again, a common mistake is that students will forget about that negative and they'll say, well, negative 10 squared is negative 100. No, it is a positive 100. And if I subtract 90 from it, I get plain old 10. Boom. Only a few left. If I take f of 3, if I look right here, okay, so I'm going to say f of 3. I'm going to take my negative sign, and again, simply by putting in a set of parentheses, I almost made that 3 negative on accident, I catch myself from making very common and very easy mistakes. When I put the parentheses in here, it made it abundantly obvious that I'm going to square this and then make it negative. Remember, we follow order of operations. 3 squared is 9, and then I make it a negative 9 minus 16 times 3. Then I say, okay, -9, -6 times 3 is -48, which is going to net me a -57. Again, a very common mistake is that students will forget about that negative, or they'll try and push that negative in there and square a -3, and they'll get a +9. Make sure that when we put parentheses in, that helps us follow order of operations. Let's try one that is a little more common of a mistake, because what happens if there's a negative and a negative? This is another mistake that students often make. Now, this is going to be the same problem, but instead of inputting a positive value, we're inputting a negative value. So I have an f of -2, and in this case, I'm plugging in a negative into a negative. And we all know that a negative times a negative is a positive, right? Awesome. So what the students will do is they'll say, well, this is already negative. When I go to square that, shouldn't I just ignore it? Or wouldn't that make it a +2 squared? Well, not necessarily. Remember, we're going to perform order of operations first. So I square the -2, which makes that a +4. And then I apply that negative and I distribute it in. So negative times 4 is -4. 11 times -2 is -22, which gets me a -26. Awesome. And so the last one, just to make sure that we know how to do the same thing with fractions, and kind of a set of fraction review, we got this one. So go ahead, pause the video for just a moment, try this one, and see if you get the same answer. Okay, so let's take a look. Plugging in the -3/2, I'm going to get 4 -3/2. I'm going to square that, plus 8 times -3/2. And so what I get is anytime I square something, remember I'm writing it out twice. -3 times -3, 2 times 2. Another way to see this is if I take -3/2 and I square it, -3/2, -3/2. Well, -3 times -3 is actually -3 squared. 2 times 2 is actually 2 squared. So I get to square each number. So -3 times -3 is going to get me a +9/4. Plus, okay, and if I do this, I get -24 all over 2. And if we remember, we have a shortcut that we can do here. If I take 9, multiply by 4, and divide by 4, we can do what we call cross-reducing. And what is cross-reducing? Well, cross-reducing is saying that if I were to perform this operation, and I were to take 4, put it over 1, and multiply it by 9 over 4, well, that's 4 times 9, which is the same thing as 9 times 4, correct? Nothing has changed. And what does 4 over 4 do? Well, 4 over 4 reduces, which is what we call cross-reduction. If I were to swap the order of which I wrote some of these things in, as long as they're all connected via multiplication or division, I can go ahead and change the order, cancel them out. Which leaves me with 9 minus 12, which is a -3. There we go. Boom. Okay, so today what we're doing is we're evaluating a function, but we're evaluating a function in a piecewise format. And now, this is important. It's not really much more difficult than what we did previously, but the idea is that we have domain restrictions listed after each piece. So typically what you would do is you would say, hey, I'm going to take this and I'm going to plug in my 5. And what we did the other day was we said plug 5 in wherever we see an x. You'd say, okay, f of 5 is equal to bracket 1/2 of 5 and -5. And we'd pause and we'd say, hey, hold on. I'm about to get 2 answers. Now I know I cannot call it a function if I get 2 answers. For every 1 input, I must get 1 output. In this, I'm plugging in 1 thing and getting 2 things back. Well, let's see what's going on. Well, for here, I can only plug in values that are less than -2. And for this bottom one, I can only plug in values greater than or equal to -2. So I have to do what I call checking the domain. So check the domain. Is 5 less than -2? No, it's not. So 5 is not less than -2, which means I am not going to use the top portion. Is 5 greater than or equal to -2? Yes. So I'm going to plug my 5 in to the bottom, which means that my function is as simple as saying, what is -5? F of 5 is -5. Boom, and there we go. I don't plug it into everything, I only plug it in where appropriate, and then I ignore everything else. So with this one, I only plug it in where appropriate. If I go and check, -1 is less than 2, so I'm going to be using that function. -1 is not greater than or equal to -2. I'm not going to be using the bottom function. So I'm going to take my f of -1, and I get 7 absolute value of -1. Which is 7 times 1, which is a positive 7. Boom. There we go. And remember, we don't actually touch the left-hand side of the equation because that is the name of the function and what we plugged in. This isn't actually performing any operations over there. Works the same with fractions. I'm going to check the domain and see 5/4 where it falls. Well, remember 5/4 is just over 1. It's actually like 1.25. So I'm going to check, okay, good, these are negatives. 1.25 is not less than that. So I'm not going to plug it into the top one. I can, apparently, I can plug it into the bottom one. Decided to cut my yes off early there. F of 5/4 is equal to -48. Open up a set of parentheses, 5/4 squared. And what we covered yesterday, we remember the fact that if I square a fraction, I'm squaring the top and squaring the bottom. So 5 squared is 48 times 25, and 4 squared is 16. The other thing we also covered about cross reduction is that I can write this whatever way I want. If I want to write it as -48 over 16 times 25 over 1 and just swap the bottom 2 numbers, well, then that allows me to take 48 and divide it by 16, which I know is just a plain old -3. So I'd end up with a -3 over 1 times 25 over 1, which makes that a -75. Boom. And there we go. So let's try a few more that might have some complexities to them. Now, when we deal with square roots, if we remember, square roots are going to give us 2 possible answers. So I'm going to check the domain, and I'm going to say, where does 3 fall? It's not less than -3. It is between these 2, so I can use that one, but it's not greater than 4. So I must be using the middle one. And so what I end up with is the square root of 3 times 3. The square root of 3 times 3 is going to be the square root of 9. And so when I say, what is the square root of 9? Well, what 2 numbers multiply to give me 9? And most of us say 3. And that does equal a positive 9, but there's another two sets of numbers, a -3, which will also equal a +9. They both equal the same thing. So when I take the square root of 9, I give it both the positive and -3. So I actually get two answers. Perfect. So let's go ahead and let's take a look at this. So f of 0. I check my domain. 0 is not less than -5. 0 is between these two. And 0 is not greater than 1. I'm going to plug in my 0. It's 2 over 0. And we run into a problem. I can't plug 2 into nothing. So what we say is that when we try and plug 2 into something that doesn't exist, this function is actually undefined. And we'll go over later in rational equations what ends up happening here, because we actually do start approaching at least one number. In this case, we're going to approach two different numbers, which is why it's undefined. We're looking at some sort of dimensional constraint that we can't overcome simply with a 2. So we'll get back to that one later on. And the last thing that you might see is if I check my domain and I see a 1, I notice the fact that 2 of my domain restrictions have a 1. First off, it's not less than -3. But I really have to check my signage because it is included in this one. 1 is less than or equal to 1, which means I'm going to be using the middle one. Common mistake might be to plug it into both of these, but 1 is not greater than 1. It is almost, so almost, but no. That one's just a flat no. So I can plug it into the middle one. F of 1 is equal to the absolute value of 1 plus 1. So f of 1 is equal to 1 plus 1. F of 1 is equal to 2. Boom. There we go. And that's it. So today we're being graphing with a graph with a limited domain. Now, a domain limitation means that I'm going to give my graph a starting point and an ending point, typically shown what looks like what commonly can be perceived as a coordinate, but with a domain limitation, it's saying, hey, I only am caring about the values, what the graph looks like between these 2 points. And now, because it is domain, we're looking at the x values. So I'm saying between what 2 points. I'm not asking between what 2 coordinates. Now, today we're showing this with interval notation. And an interval notation means on the actual border, if I want to include that point, I'm going to put that number in brackets, like shown right here. I'm going to include the -4 and include the 2. If I don't want to include it, I'm going to include parentheses, just like what I see right here. I'm not including that point, and I'm not including that point. So let's see how this is done. Now, what I would do, I typically graph these with a pencil first off, so that I can erase the portions of the graph that I don't need. Because again, we're only concerned with part of the graph. So I'm going to graph this. This is a standard line. I have an intercept at +1, and I go up 3 and over 4, down 3 and back 4. Now that's going to give me a straight line just like this. Again, I'm drawing this very lightly because I'm going to be erasing this here in just a moment. Now, the other thing is I'm only concerning myself from -4 to +4. So what's going to happen is I'm literally going to say, okay, from -4, 1, 2, 3, 4, I'm going to erase everything on the outside. I don't care about that portion of the graph, so I'm going to erase it. And I'm only going to go to +4, which means I'm going to take this and move it over 1, 2, 3, 4. That means I don't care about anything over here. I'm going to erase it. Boom. So that's the only portion of my graph that I want to keep. And then am I going to include the -4? No. So I'm going to put an open circle. Am I going to include the +4? No. It's going to be an open circle. So what I end up getting is this is my equation. It goes from this point, increases at a rate of 3/4, and stops right there. Done. So let's try it with included points this time. So again, I'm going to start out with a pencil so that I can erase it. See, I'm going to start at -1. I'm going to go down 1 and over 2, up 1 and back 2. And I'm going to connect them with a solid line. Again, I'm drawing this very lightly because I'm going to be erasing a good bit of the graph. The next thing is I'm saying at -4, I don't want anything before that. That's my starting point. So I'm going to take it and go back 1, 2, 3, 4. I don't want anything over here, so I'm going to erase that little piece of the line. That no longer exists. And then I'm going to go to 2. So I'm going to include the entire graph all the way up until that part. So I'm going to go from 1, 2. So none of that portion of the graph am I going to include. So I'm going to go ahead and I'm going to erase it. So I only have that little piece. This time though, the point at -4, I'm going to include. So I'm going to shade it in. And the point at 2, I'm going to shade in. And I'm going to shade in the entire line given my domain restriction. So boom. I have a line segment with a start and a finish from -4 to 2. So why don't you pause the video, try and do this one on your own, and then resume play once you've finished. Okay, so let's take a look at this. I'm going to pull out my pencil. This is a line with no y-intercept. So it starts here, up 2 over 1, up 2 over 1. I go down 2, back 1, down 2, back 1. I'm going to connect this with a solid line. Draw it very lightly so that I can erase it later on. And now, one of the things that I noticed when I start with my domain restriction at -3, -1, -2, -3, I don't have any graph here, which is going to present a problem because if I want to see where the graph is given this domain restriction, I can't see it. So I'm going to have to change my scale. So I'm going to scale this graph by 2. So my y is each by 2, and my x is by 2. And what you might ask is, well, wait, wouldn't that change how the graph is shaped? No. If I change the scale of both, this is a straight line, it's going to continue to be a straight line. Instead of going up 2 over 1, up 2 over 1, up 2 over 1, I still hit the same point by going up 4 over 2. Because we remember that 2 over 1 is equal to 4 over 2. So the slope looks the same. But what it allows me to do is that it allows me to get that -3 on the graph. So 2.5 blocks, 1.5 blocks is going to get me that -3. And so I'm going to erase everything before that. It's going to give me a point right there. And then I'm going to go over 1, which is going to be half a block, and I'm going to erase everything over here. So all the way up to right at half, right there. So now at -3, I have a point right there. At 1, I have a point right there. I'm going to connect them. So it's only that little piece of the graph, and I'm going to include when I hit this boundary. Done. This boundary is not included. There we go. So, now, does domain restrictions only work for lines? Well, let's give an absolute value a shot and see what we notice. So, I know this is the parent absolute value function, which is going to give me a straight diagonal line and a straight diagonal line in both directions. Again, I'm not going to draw it very dark because I'm going to be erasing it. I know I'm only going to be including it from -4. So 1, 2, 3, 4, and I will erase it. Erase that little piece. There we go. And I'm going to stop at 2, so I'm going to take it and go 1, 2. And I'm going to erase all that. That no longer exists. I cut it off the graph. And so my graph this time goes from here to here with only the left point included. So I'm going to go ahead and trace over my graph for the actual portion of the graph that I'm going to keep and shade in that point. Done. So the only way that this could possibly get any more complicated is what happens if we have an infinity? Well, let's think about that. So my starting point is at 0, and my ending point is at infinity. It sounds like the graph is going to have a start, and can we ever actually reach infinity? No. So are we ever actually going to end the graph? Also no. Perfect. So let's go ahead and let's graph this. I know that inside the brackets, that's going to be a right movement. So I'm going to take that V and shift it to the right by 2 units. The slope remains unaffected. It's still a perfect diagonal. But we notice that the parent graph has been shifted to the right by 2. And then the next thing, I'm going to start at 0, which means on the origin, I'm not going to include the left hand. None of this is included in the graph. Let's go ahead and erase all of it. Nothing before that line. But the graph does continue to the right, and in fact, it never stops. So if I put my circle, I'm going to shade in this portion of the line, and because it doesn't stop, remember, we just have to end the graph with an arrow which says, hey, this graph continues in that direction. Perfect. My 0 point is not included. Okay. And for the next one, what happens if I don't have a starting point, but I have an ending point? Well, let's take a look. This absolute value function has been shifted down by 3. So I know 1, 2, 3 starts right here. And that 3 in front of it means that this is the slope to the right. So I'm going to say, okay, the slope to the right is up 3 over 1, up 3 over 1, up 3 over 1. And then I'm going to mirror that on the other side. Up 3 left 1, up 3 left 1. I'm not going to continue down because the absolute value does bounce. It does have a V shape, which is going to allow me to do this. Has a V there. Has a V right there. Cool. So again, I'm drawing this very lightly because I'm going to be erasing, well, I'm not going to be erasing anything over here, but I am going to stop at 1, which means none of this gets included. So let's go ahead and erase all this hard work we did over here. Turns out this was for naught. So anything after 1 just gets erased, which means that my point at 1, I have the bottom of the V, and it goes up, 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 and away, and continues on by putting an arrow. Now that 1 point I actually included. There we go. Now, the last thing I might ask before we end is, can we actually have, so can we have an interval such as negative infinity to 1, or like we did on the upper one, let's say 0 to infinity. Can we actually include infinity in our interval? Can this happen? Think about that. When we have the brackets, that means we include the point. So we go all the way up to that point, and that's part of our graph. You're going to ask yourself, can you actually trace the graph to infinity? If your answer is no, then we cannot include. No. Infinity is unreachable, and so is its point. Because infinity is unreachable, we cannot include graphs like this. It does not work. Infinity always has to be a parenthesis because, again, infinity is something we could never reach. And that's all we got.